Once, if we are thorough with laws of logics, we can see its application to switching circuits. A switching circuit is basically made of wires and switches. Connected between two terminals. Let me consider the switching circuit in which P is a switch connected between the two terminals T1 and T2, and we can note that current flows provided the switch P is closed. If switch is open, current doesn't flows. Let me consider two more situations. If I consider this switching circuit, we can note that current flows from T1 to T2 provided both the switches P and Q are closed, and we say P and Q are in series connection, and this one is representing P conjunction Q. And if we consider this, we can note that current flows from T1 to T2 when at least one of the switches closed. So this represents P disjunction Q, and we say P and Q are in parallel connection. So now if I consider any switching circuit, it will be a combination of these three. Now let me try to understand how to simplify the given switching circuit with the help of laws of logics. Simplify the following switching circuit. Under this heading, the main task is writing a logical expression representing this switching circuit. We can note that here the switching circuit is basically made up of two circuits connected in series. These two connected in series. And if we come to this part, we can note that these three are in parallel connection and these two are in parallel connection. And if we just get into this part, these two are in series connection, these three are in series connection. In this case, these three are in series connection. Now let me write the logical expression to this. Basically, as I mentioned, this should be in one bracket and this is in another bracket, separated by a conjunction. Okay. And these three are in parallel connection. So we are saying that P is in disjunction with this expression. So this is conjunction between P and Q. And these two are in parallel connection. So it is disjunction. And these three are in series connection, that is P conjunction Q conjunction negation R. Conjunction. This part, so these two are in parallel connection, but these three are in series connection. So it is P conjunction R conjunction T disjunction T. The next part is simplifying this. As I mentioned already, this expression is in conjunction with this expression. Now, if we are just handling this part, here we can note that this is my P, this is Q, this is R, separated by a single connective disjunction. Which means associative law is valid here. And you can note that if you just come inside this expression, associative law is valid once again. Because conjunction with three statements. Here also conjunction. So once again here associative law valid. Let me use associative law and rewrite them. So when I'm doing this, I'm just preparing it for the next step. That is, I just want to use absorption law. So where, since associative law is valid here, I can group these two or these two. So what I will do, I will use associative law on this. I will group. Now I will group these two. That is P disjunction, P conjunction Q disjunction, P conjunction Q conjunction negation R. Conjunction. Here once again, I can use associative law to rewrite this one as P conjunction R conjunction T. When I am using associative law, I am preparing the problem for the next step which I am supposed to use. Here I have used associative law in such a way that I can use absorption law. Just observe this: P outside, P inside with two different connectives. So I should rewrite this one as just P disjunction. Okay, this whole expression becomes just P disjunction. And here once again associative law is valid, and you can know that P is there inside as well. So what I will do now, I will use associative law to rewrite this one as P conjunction Q conjunction negation R, so that in the next step I can use absorption law to write this entire expression as just P, and this is conjunction. And look at this part here: T outside, T inside with two different connectives. So this just represents T. So in this step I used absorption law. So this is logically equivalent to P disjunction, as I mentioned already, P outside, P inside with two different connectives. It just represents P conjunction T. This is once again from absorption law. And you can note that in this expression we will find P only once, T also appeared only once. So this is a simplified expression, and I can write the switching circuit corresponds to it. This represents P and T are in series connection between the two terminals T1 and T2, which means I can replace this switching circuit with only two switches P and T connected in series between the two terminals T1 and T2. Now let me consider the next example. So this one basically what is in parallel connection. So this is one circuit and there is a second circuit. So these two are in parallel connection. So which means it is basically conjunction between two switches. It is basically conjunction between two networks. Okay, so which means that I should get disjunction between. But these two, so this P is in series connection with this, and this circuit is in series connection with this. So now if we just open this bracket, here we are writing that P is in series connection with this circuit. So in this circuit these three switches are in parallel connection. So negation R, disjunction Q, disjunction, negation Q. Let's close this bracket, and this is in disjunction with. So these two are in series connection, but in which this network is in parallel connection. R, disjunction, T, disjunction, negation R. So this is in conjunction with negation Q. Now let me simplify this logical expression. If I just observe this, I can't use the absorption law for sure because P is there outside, there is no P inside. But you can note that Q and negation Q is there here. So which means if I just group Q and negation Q, that is possible because of the associative law in this. I can do that. I can use inverse law in the next step. And if I come to this one, you can just swap R and T by using commutative law. As you have got disjunction here, you can group R with negation R to use inverse law again in this. Let me do that. So it is P conjunction, me write the flower bracket, negation R, disjunction, Q disjunction, negation Q. Disjunction, we open this bracket, so T disjunction, R disjunction, negation R, conjunction, negation Q. In this one, basically I have used associative law, along with I also used commutative in this place. So this is logically equivalent to. So by using inverse law, this is P conjunction, negation R, disjunction, Q disjunction, negation Q. One of the statement is always true. It's a tautology. Disjunction, open this bracket. Here it is T disjunction, R disjunction, negation R. Once again it is tautology, conjunction, negation Q. In this step we used inverse law. And this is logically equivalent to P conjunction, negation or disjunction T naught. So since we are dealing with a disjunction, one of the statement is true, it has to be tautology here. It's T naught. Disjunction, it is T disjunction T naught. Once again T naught is dominating, it's domination law, T naught conjunction, negation Q. So this comes from domination law. And this is logically equivalent to P conjunction T naught. It has to be P disjunction T naught conjunction negation Q. It has to be negation Q. In both the places I used identity law. And you can note only one P, only one Q in this expression, which means, so this is in simplified form, and we can write the switching circuit corresponds to it, and it has to be a parallel connection. It's P, this is negation Q between the two terminals T1 and T2. I hope it is clear to you people. Thank you all.